Alrighty there, people. Welcome. We're going to do a little review here of some mechanisms that you're responsible for. Let's take a look, first of all, at this first one here, which is going to be SN2. You'll notice that this is a primary halogenoalkane, and I know it's primary because this carbon that the chlorine is attached to only one other carbon. So that makes it a primary carbon, therefore it's a primary halogenoalkane. And there it is there, written in a slightly different way to kind of highlight its three-dimensional shape, which we'll be learning more about in Chapter 4. That is your starting product. The nucleophile is a hydroxide ion, which is a negative ion, and it's that extra electron, that pair of electrons that make up the negative charge, that is going to attack the carbon. Just a little curly arrow, just like that. And that is going to give rise to a transitional species that has 5 bonds on that central carbon. So there's a hydroxide attached itself to that central carbon with the chlorine still there. We still have these 2 carbons up top here, and then we have those 2 hydrogens that are kind of down below into and out of the page. So there's my 5-membered ring, or 5-membered compound, pardon me. And of course this whole thing has a negative charge, so you can kind of put brackets around it saying there's a negative charge there if you like. Useful to have. And then what's going to happen now is this pair of electrons is going to jump out and leave, so the umbrella kind of flops over, and that gives you your end product, which is a primary alcohol now. So there's my carbon, and then my carbon chain of 3, and then of course I have my 2 hydrogens here. And of course I'm not drawing these other hydrogens here, but they're all over the place over there too. That is your SN2 reaction. Remember the SN2 reaction, the halogen attacks first, and then the leaving group, or the halogen, leaves. And then in SN1, the leaving group leaves, the halogen leaves first, and then the nucleophile attacks. And that happens for tertiary halogenoalkanes. And then primary and secondary halogenoalkanes undergo both SN1 and SN2. So to summarize, this is going to go by way of SN2, and this is going to go by way of SN1, and this will go by both. Okay, just keep that in mind. Okay, moving down to the next one, which is going to be our free radical substitution reaction, which I can bring it to the screen. There we go. So we're looking at the bromination of methane. This is not normally a spontaneous reaction. You'll know that bromine is used to react things, or to react with alkenes, to test for the presence of alkenes. But with alkanes, it's not spontaneous, so that's going to take the 3 different steps to get to our product. So the very first step is initiation, which involves heterolytic fission. Sorry, I always get that wrong. It's homolytic fission. We're going to create 2 identical radicals. And that is the reaction there. If you really wanted to, you could say, okay, well, I have an electron going that way, an electron going that way. The bond splits up equally, and that gives my 2 bromine radicals. Okay, for propagation reactions, we're going to be making more radicals, and people always ask me, how do I know what it reacts with? Keep in mind, there are really only 2 different molecules around at this point, methane and bromine. And so the bromine radical is going to react with one of those. And if it reacts with another bromine molecule, I'm going to get bromine and another bromine radical, right? Like I'll get a little bond formed here. This will go that way. That'll go that way, like that. And so, in other words, I don't get anything different, so I don't really care about that one. Okay? What I do care about is this bromine radical with the methane. That's what I'm going to be focusing on for this next step. Okay, so there's my methane molecule, CH4, but I've drawn it with the H sticking out front because the H's, of course, are on the outside. They're most exposed. It's what the radical is going to grab onto. Okay, and so I know that I'm going to get a bond forming between these 2 here. So this 1 electron goes there. I need a second electron to make that bond. It comes from the CH bond, leaving an unpaired electron on that carbon there, giving me my product, HBr, which is an unwanted product, and the methyl radical. It's the methyl radical that's important here, because that's going to go on into my next step. Now again, what else is around? Well, I have a methane molecule, which would just give me another methyl radical and another methane molecule if those 2 reacted. And I have a bromine molecule that I could react this with. So let's do it with the bromine one. Okay, and that is going to give me my desired product. So I'm going to get a bond forming here. This 1 electron goes to make that bond. I need a second electron to make that bond. leaving an unbonded electron on that bromine. So there I have my desired product as well as another radical. Okay, so I have these two radicals formed and then my desired product. I also have this unwanted radical I don't really care about, but it is there. I don't want to completely ignore it, but I just don't care about it. Okay, and for termination steps, what we want to do is we want to get rid of radicals. And when two radicals come together, we have two unpaired electrons coming together, which makes a pair of electrons, and that's what we want. So I'm going to have any combination of those two radicals, okay? So either two bromines, two methyls, or a bromine and a methyl. Those are my three possible termination steps. Two bromines would just give me a bromine molecule, simple. Two methyls would react and I would get an ethane molecule. Again, it's unwanted like the HBr, but I'll get it. And lastly, we'll get our desired product, bromomethane, by reacting the two mixed there, a bromine and a methyl radical. So that is the complete mechanism with curly arrows and everything. And hopefully that answers all your questions about those.